Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to understand the topics of sampling theory and linear regression analysis, and we are going to continue with our module on the linear regression analysis, and we are going to continue with our chapter on the multiple linear regression analysis. So, you can recall that in the earlier lecture I have given you a brief background about what is multiple linear regression model and what are the basic assumptions, what is the setup, how are we going to collect the observation, how are we going to represent them in the form of vectors and matrices, and so on. So, now in this lecture I am going to estimate the parameter beta, but before that you have to go back to your lectures in simple linear regression model, and you have to recall that how we have done the estimation of parameters beta 0 and beta 1. We had used the principle of least squares and maximum likelihood estimator, and we had minimized the sum of square due to random errors. So, now exactly the same thing I am going to follow here in the case of multiple linear regression model, but how to do it, that is my objective in this lecture to explain you, because I had told you earlier that please try to have this simple linear regression model very clearly and try to understand the basic fundamental. They are looking very simple, but they will be used in the case of multiple linear regression model. So, if you have not done it, so better is to go back and try to have a look, and then you try to watch this video. Okay, so let us begin our lecture. So, now we are going to consider the principle of least squares and method of maximum likelihood estimation for the estimation of the parameters beta and sigma square. So, you may recall our model was y is equal to x beta plus epsilon, where y is a n cross 1 vector of observation on the response, x is a n cross k matrix of explanatory variable in which n observation on each of the k explanatory variable have been obtained, beta is a k cross 1 vector of regression coefficient, and epsilon is a n cross 1 vector of say random errors. Now, in case if I try to employ the principle of least square, then the least square estimator which we are obtaining for beta is given by here b is equal to x transpose x whole inverse x transpose y. So, you can see here x is known to us, y is known to us, and so we can estimate this parameter beta. And you can see here that this expression, this is of order here, x transpose here is k by n, x is n by k, x transpose is k by n, and y here is n by 1. So, b is going to be a vector of order k by 1. Essentially what b is doing? This b is going to be something like b1, b2, bk. And what b is doing? B is trying to estimate the parameter vector beta, which was beta 1, beta 2, beta k, right. So, b1 is the estimator of beta 1, b2 is the estimator of beta 2, and so on. So, you can see here now the estimators are in the form of vectors, right. But when I am saying that estimator of beta 1 is b1, estimator of beta 2 is b2, it does not mean that they are independent, right. This is a joint of joint estimator of beta 1, beta 2, beta k, right. So, because this is a vector quantity. So, all b1, b2, bk, they are not really independent in general. Okay. So, next is our estimator of sigma square. Once you have obtained the beta vector by b, then we have to replace beta hat by b, and we can write down the sigma square hat as y minus x
B transpose y minus x B. This is the symbol here, this is transpose, you know it, transpose of a matrix or a transpose of a vector, and this is divided by here by n minus k. So, n is the number of observations and k is the number of explanatory variables. So, now you know y, you know x, you know b, you know n, you know k. So, you can estimate this sigma square, and the estimated value will be indicated by sigma square hat. So, these are the two results which we are going to consider, and yeah, I will try to show you the proof also. But what you have to consider, that when you consider the simple linear regression model, then your beta vector was something like beta 0 and beta 1, right, and similarly you had obtained this here beta hat 0 and beta hat 1 as b 0 and b 1 respectively. And when you consider the estimate of sigma square in the case of simple linear regression model, then this divisor was actually 2, means here k was equal to 2. Why k was equal to 2? Because you were writing the model beta 0 plus beta 1 x as beta 0 times 1. So, that means you had two explanatory variable, one was variable which always takes the value 1 and another was your x. So, that is why it was k plus 2. So, remember the point which I am trying to emphasize, which sometimes create a confusion among students, is that the divisor in the case of estimator of sigma square is given by 1 upon number of observations minus number of explanatory variable. Now, in any case, if the number of explanatory variables are more or less, they are denoted by different formula, different expression, then we can adjust them accordingly. Right. Okay. So, now let me try to give you here the basic idea behind the formulation of this estimator and its proof. So, you can recall the least square estimation in the case of simple linear regression model y is equal to beta 0 plus beta 1 x plus epsilon. Right. So, so you may recall that we had a line which we expected to fit here like this, and then we had the observation which are lying on this line, they were denoted by capital Xi yi. All these observations will satisfy the line y is equal to beta 0 plus beta 1 x, and then we had observed those points at the same value of x, and the observed value was obtained somewhere here, which was on the upper side of the line, and the observed points were denoted as small xi and small yi. Right. So, and then what we had done, we had minimized the difference between the observed and true values, or we had minimized the vertical distance between the line and the observations, and we had minimized the sum of squares due to error. If you remember, you had minimized summation epsilon I square, I goes from 1 to n, and you had denoted by s beta 0, beta 1 and so on. You had differentiated, used the principle of maxima and minima, and then you had obtained the values of, or the estimators of beta 0 and beta 1. So, now the same thing is going to be followed here also. Now, the estimator of beta, suppose I denote this is my parameter and this is being estimated by beta hat, and the ordinary least square estimator of this beta, which is beta hat, is going to be denoted by symbol b. I am using here the symbol b, not beta hat, because I want to extend the same symbol that you have used in the case of simple linear regression model. Right. So, suppose the estimator of beta obtained by the method of least square estimation is obtained, and this is denoted by here like this. I am using here transpose because now I am writing it here as a row vector. So, essentially here this b is something like b1, b2, bk. So, I am connoting by b the k cross 1 vector of the ordinary least square estimator of beta 1, beta 2, beta k, which are in the form of a vector. Okay. So, now essentially we have to obtain this value of b. So, how to obtain this value of b? We will again use the same principle that we try to minimize the sum of square due to error, and sum of square due to error is summation I goes from 1 to n epsilon I square. Now, you have to observe one thing, that my epsilon here is something like epsilon 1, if you remember epsilon 1, epsilon 2, epsilon n. This was your here n cross 1 vector. Now, if I try to write down here epsilon transpose epsilon, what will be this thing? Epsilon 1, epsilon 2, epsilon n, and epsilon 1, epsilon 2, epsilon n. Now, if you try to multiply it, this will be epsilon 1 into epsilon 1, that is epsilon 1 square, then epsilon 2 into epsilon 2, that is epsilon 2 square, and their sum. So, this will basically become epsilon 1 square plus epsilon 2 square up to here epsilon n square. So, this is nothing but your summation epsilon I square, I goes from 1 to n. So, what I try to do here, I try to write down the epsilon transpose epsilon here as in place of summation epsilon I square. And you will see that once I try to write down these quantities in the form of vectors and matrices, then many of my algebra will become very simple to understand, and the expressions are easy to found. So, now, I will write here like this, and now I am writing epsilon here as a y minus x beta, right. You remember y was x beta plus epsilon, and then I try to write down here this y minus x beta in place of epsilon. So, this is your here epsilon transpose, and this is here epsilon, and the values of y and x are given to us. So, what we try to now do, our objective is this: we would like to minimize this function s beta, which is summation of epsilon I square, and we would like to obtain the value of beta such that the value of beta minimizes this sum of squared deviations, right. So, the question comes, what is the guarantee that the minimum will always exist? The minimum will always exist because s beta is a real valued convex and differentiable function, right. So, what I can do exactly on the same lines as we had used the method of maxima minima in case of simple linear regression model, here also I will use the same principle. So, I try to expand this y minus x beta transpose, y minus x beta, which is equal to here y transpose minus beta transpose x transpose and y minus x beta. So, I try to multiply it, and whatever is my outcome, this is given here. So, you will see here that s beta will come out to be like this: y transpose y plus beta transpose x beta minus twice of beta transpose x transpose y. Now, what we have to do? I simply have to use the principle of least square. So, I try to differentiate this s beta with respect to beta vector. Now, remember one thing, here we are using the differentiation with respect to a vector. So, in order to do it, first I try to show you the result which I have used, which is available in all the results related to the linear estimation. So, if there is a quadratic function, say f z, and my variable here is capital Z. So, if the quadratic function is of the form z transpose is z, where z is a m cross 1 vector of real values and A is any m cross m symmetric matrix, then the partial derivative of this quadratic function f z with respect to z can be obtained by like this, twice of A z, right. So, this is the same result which I have used here, and after, so then so the differentiation of y transpose y will become 0, and the differentiation of this quantity beta transpose x beta will be twice of x transpose x beta, and the differential of twice of beta transpose x transpose y is twice of x transpose y. And yeah, means just I am trying to obtain the second differential also, because that will be used to determine whether the obtained equation is providing the maxima or minima. So, just to be so I am just finding out the second derivative of beta, with respect to beta vector here itself. So, this quantity comes out to be twice of x transpose x. So, you can see that this quantity is independent of beta, and this transpose x matrix, this is going to be at least non-negative definite always, right. So, that will ensure that whatever the value of beta which we are going to obtain by solving this normal equation, this is my here normal equation where when I try to put it equal to 0, right. Whatever the solution I obtain from this equation, that is going to minimize the function s beta, that is the sum of squared deviations due to random error, right. So, if you try to put this partial derivative of s beta with respect to beta equal to 0, then we get the normal equation, and if you try to solve it, this is trying to give you here like this twice of x transpose x beta minus twice of x transpose y is equal to 0, or I can write down here x transpose x beta is equal to x transpose y. So, I can now say here let B be the solution for beta from this equation. So, I can write down that solution will satisfy this equation. So, x transpose x b is equal to x transpose y. Now, I need to find out the value of b. So, what I can do? I can pre-multiply by x transpose x inverse on both the sides. So, this will become here like this x transpose y. So, now this part becomes here identity matrix I, and so this b will come out to be like this x transpose x whole inverse x transpose y, which we have obtained, which is called as an ordinary least square estimator, right. Okay. So, now if you try to look at the structure of this ordinary least square estimator, you can see here this is involving a quantity x transpose x whole inverse. Now, under what type of condition this inverse will exist? So, we know that this inverse is going to exist only when rank of x matrix is equal to k, that is it is full column rank, because only under that condition this x transpose x matrix will become a positive definite matrix, right. And that is the reason, if you remember, we had made one assumption that rank of x is equal to k when we made different assumption for the multiple linear regression model. So, by assuming that rank of x is equal to k, we can ensure that x transpose x matrix is a positive definite matrix, and hence the inverse will always exist, and thus the least square estimator of beta can be obtained by here b. Okay. And we already have seen that the second partial derivative of s beta with respect to beta, this is also at least non-negative definite. So, now I can assure that b minimizes s beta. So, this is our ordinary least square estimation. So, now onwards, whenever we are trying to do anything in this course, we will always assume that x is a full column rank matrix. Well, just for your information, I can also share this information that it is possible that x may not be a full column rank matrix, and yeah, this also happens. That means all the columns of x1, x2, xk are not independent, they have got certain relationship. For example, if you try to take here 3 variables here x1, x2 and x3. So, x1 is suppose the income, and x2 here is saving from that income, and x3 here is expenditure, right, from this income. Then you know that x1 is equal to x2 plus x3, right. Okay. So, now under this thing, this x1, x2, x3, 3 variables which you are taking here k equal to 3, all these variables will not be independent, and the rank will be only here equal to 2. So, in that case x will not remain as a full column rank matrix, and this problem is actually termed as problem of multi-collinearity. So, I am not saying that this problem does not occur in practice. So, I am assuring you, yes, it may happen that the data may have such an issue. Under those conditions, we have 2 options, that either we try to use the tools for the multi-collinearity, or we can obtain the generalized inverse of x transpose x. So, the generalized inverse of x transpose x is obtained in a different way than the unique inverse of x transpose x. I am not going into those detail, but I am just informing you just that it is possibility, that this possibility is there, but definitely the generalized inverse can be obtained in different ways, and except one which is called as Moore-Penrose inverse. Moore-Penrose inverse, all other inverses are not unique. So, it is possible that for the same data set different people may obtain different values of beta using the generalized inverse. Well, I am not going into those detail, but my objective was simply to inform you, to update you. Okay. Now, you remember that in the case of simple linear regression model, once we had obtained the value of beta 0 as b0 and value of beta 1 as b1, then we had obtained the fitted model just by replacing beta 0 by b0 and beta 1 by b1x. Now, the same thing I try to do in the case of multiple linear regression model. Now, you see, now you cannot blame me that I am not explaining anything, because I already had told you during the lecture of simple linear regression model that please try to understand these concepts very carefully, because I will be using them there directly, right. So, working on the same line, if you remember, we had simply replaced the estimated value of the parameter in case of the or in place of the true parameter. So, same thing I am trying to do it here. So, our model was y equal to x beta plus epsilon. Now, I am trying to estimate this beta by b. So, I can replace this beta by b and I can write down y is equal to bx. So, this is our fitted line, or this is the fitted linear regression model, right. And after this, if you remember, in the case of simple linear regression model, we had taken the values of x, and then using the fitted model, we had replaced the value of x say by x0 in the fitted model, y equal to say b0 plus b1 x0, and this value was called as fitted value y hat. You can recall that we have taken several examples to explain you. So, now the same concept I am trying to extend it here, and the fitted values for a given x here, they are denoted by here y hat, and they will be xb, right. So, I am using the same x over here, but now I am trying to obtain the value of y which are obtained through the fitted multiple linear regression model. And if you try to do it, if I try to replace here the value of b, which is x transpose x whole inverse x transpose y like this, then I can write this y hat something like this hy. So, what I am doing here, that I am writing this matrix, this component of this expression x transpose x whole inverse x transpose as h, right. Actually, this h is a very important matrix in regression analysis, particularly in multiple linear regression analysis. This matrix is called as hat matrix, right. This is called as a hat matrix, and hat matrix has a couple of properties which helps us in making very useful statistical inferences. This matrix H, which is hat matrix, is symmetric. This is idempotent. That means, if you try to multiply H into H, you can see here, if you try to write down here x transpose x whole inverse x transpose, which is your here H, and if you try to repeat it here again x transpose x whole inverse x transpose, this is here another H. So, you can see here x transpose x into x transpose here x whole inverse, this becomes here I. So, now what are you getting here in the next step? X transpose x whole inverse x transpose, and this is same as here H. And similarly, if you try to find out the trace of the matrix H, then this is obtained by using the result. If you remember, there is a result in matrix theory which is something like trace of AB is equal to trace of BA, right. So, in those cases what I am trying to do here, that I am trying to find out the trace of here matrix H. So, I write it here say here H, and then I try to write down this matrix here as say A and this matrix here as say B, and then I try to use this result, trace of AB is equal to trace of BA. So, you can see here this is your here B and this was your here A. So, now you can see here that this matrix here is X transpose X. So, X transpose X into X transpose X whole inverse, this is identity matrix of order k by k. So, we have a trace of I k, and trace of I k is something like you are trying to write down 1 1 1 1 1 here k times. So, k into k matrix. So, this is going to be 1 plus 1 plus 1 up to k times, which is k. So, these are very important results that you will see that we will be using them, and you will also use them in further lectures. Now, from the results that we obtained during the simple linear regression model, you had obtained the residuals. If you remember, we had constructed this type of figure in which we fitted this model, right. This is now under this circumstances, this is your here fitted model, and using the value of using the given value of x, you obtain the value of y. So, and the difference between the observed values, which is here y, and the values which you have obtained after fitting the model, which are your fitted values. So, the difference between the observed and fitted values of the variable is called as residuals. So, now earlier you had residuals which were scalars, right, because you are trying to obtain for every xi. Here also they are going to be scalars, but I can express them very nicely in a form using the vectors and matrices. So, if you try to see, I am using the same result which I used earlier. So, the residual vector E is now defined as y minus y hat. The only difference with respect to the simple linear regression model is that now this is a n cross 1 vector, right. So, means I am now fixing my notation that this difference is y minus y hat. So, now y hat here is y minus here y minus x b. So, y minus x b can be written as y minus this x b can be written as h y. So, this is here y minus h y. So, I can take out this y common on the right hand side, and so this becomes I minus h into y. Now, I am using another notation h bar. H bar is denoting this matrix I minus h, right. So, you can see here h bar is a matrix which is related to your hat matrix, and this hat matrix also has the similar properties what we had in the case of H. Yeah, for example, you can see here these are the properties in case of H. Now, in the case of H bar also we have a similar properties. H bar is a symmetric matrix, and H bar is also an idempotent matrix just like H, and you can see here what I have shown you here as bar into H bar is I minus H into I minus H, and if you try to open it and use the property that H into H is equal to H, you can see here this will again come out to be I minus H, which is same as H bar. And if you try to find out here trace of H matrix, so this is simply trace of the matrix identity matrix of order n minus trace of H. Trace of H you already have obtained. So, trace of this I n minus trace of H is simply your here n minus k, right. Sometimes you have to be careful, people try to make a mistake that they try to find out the trace of I minus H, and since in the case of they try to write out trace of I and minus trace of H, and if you remember that in the case of finding out the trace of here matrix H, we also had here say trace of I, right. So, people try to people sometimes get confused that this is also trace of I and this is also trace of I, but what you have to keep in mind, this was an identity matrix of order n, and now this is a matrix of this is an identity matrix of order k. So, do not get confused that trace of I minus trace of I is 0, which is wrong. So, this is equal to n minus k. Okay, so, now we come to an end in this lecture. my idea was very simple. Using the concept that we had earlier discussed in the case of simple linear regression model, I wanted to extend them to a multiple linear regression model. The only thing is this, there are small differences in the algebra, the way we have obtained the expression, otherwise the concepts and the definition, they remain the same. And you will see that these things are going to work exactly on the same line at as B0 and B1 worked in the case of simple linear regression model. So, now the next question is, you have obtained this value, you have obtained the model, you have obtained the fitted values, you have obtained the residuals. Now, how to obtain them on R console in the R software, that is our next question. So, you will see that I am going to use the same commands which I use in the case of simple linear regression model, right. So, that lecture is going to be very simple and straightforward, provided you come after a quick revision of the lecture in the chapter of simple linear regression model, where we had obtained the regression coefficient, fitted values and residuals in the R console. So, you please have a look, and I will see you in the next lecture. Till then, goodbye.